I'm SangBin. I'm a software engineer at Anyscale. Today, I'm going to present data processing on Ray. There are three things I'm going to talk today. First, I'll iterate the importance of general purpose system for ML infrastructure. Second, I'll introduce Ray and its previous limitations in large-scale data processing workloads. And lastly, I'll go through the architectural improvement we've made over the past year to overcome that. Let me start from introducing myself. I'm a software engineer at Anyscale. I have primarily worked on open source project Ray as a committer, and my current focus is to improve data processing support on top of Ray, which is why I'm having a talk today. Okay, then let's start from why we need a general purpose system for data processing. In the modern ML infrastructure, there are lots of complexities in composing different types of workload in different specialized systems. For example, this is the one I actually have seen in the industry. First, it needs to run ETL jobs using the Spark cluster, load and shuffle the data to the training cluster, which for example can use Horovod. And after that, it uses different type of systems to run hyperparameter tuning. For example, in this case, people can use RayTune and Ray for hyperparameter tuning. And sometimes the training jobs need to offload their work back to the Spark cluster because it needs some data processing work again. And there could be many other scenarios that can complicate ML jobs. Then what are the problems here? Firstly, job composition across multiple different systems can actually increase the system complexity because it requires to maintain the multiple systems. It requires you to organize the workflows, schedule jobs that are enough resources, take care of dependencies among jobs, and reason about failures. And there are many other complexities you need to handle between different specialized systems. There are so many other possible complexities. Also, at the same time, managing multiple different systems could be incurring maintenance costs. For example, people might need separate teams, and to manage the system, there's high learning curve, as well as you also need to understand each system to efficiently operate and debug. Sometimes it's also not efficient to actually operate two different systems for two different workloads, like data processing and ML workload, because in order to communicate those data between jobs, you always need to go through the intermediate layer, like Parquet files. Then what if you have a general purpose system? If a single system can run different type of workload, it can actually remove the complexity of jobs because it can actually group jobs more logically rather than type of workloads. And those different complexities, while you're composing all different systems, is going to be reduced. For example, some of pre-processing, feature processing workload can be run in the same cluster as the training workload, if that makes more sense and if they make things simpler. And second, it is a lot easier to understand and operate systems because you just need to understand a single system. You just need to understand, you just need to learn, you just need to teach one system to your team. And lastly, some type of optimization, like you just partition data in memory, just caching in the memory without actually going through the Parquet file, it should be possible with this kind of approach. So as you can see, this type of system composition could become like this with a single general purpose system and multiple libraries on top of it. Then what could be the good candidate here? I'd like to introduce Ray, because it's Ray Summit, and I'm talking about Ray. So I'd like to introduce Ray today as a solution of this problem. What is Ray? Ray is a simple library for distributed computing, which provides very intuitive APIs to actually compose this distributed computation. And it's also general purpose, so you can use the same system for different purposes, like machine learning training, hyperparameter tuning, data processing, and etc. And it's also an ecosystem of libraries, so it supports a lot of different type of workloads that usually requires separate systems normally. And it's also high performance, and it runs really well. It keeps the performance even in the large scale. So this is a simple Python program I prepared to demonstrate Ray. So as you can see, the left side, it's function, the right-hand side, it's a class. It's like very simple function and class. And in Ray, you just need to annotate function and class using ray.remote. And just by adding .remote after the function invocation or class initialization, you're able to actually execute them in the distributed systems and run them in the distributed manner. And Ray is a framework for distributed computing. It allows you to write distributed applications like a single machine program. And many distributed system problems like fault tolerance, communication, fault, the scaling, and etc. are handled by Ray. It also has many distributed libraries built on top of it, both native libraries like RayTune, RLib, and RaySurf, and other third-party integrations libraries like Modin or Desk-on-Ray, Mars for data processing, Hugging Face Space for NLP, and Horovod for machine learning training, and many others. All these features clearly indicate the Ray is a great candidate to be a general purpose system to simplify this end-to-end ML pipeline computation. For example, instead of maintaining clusters for different workloads, you can use Spark on Ray for the ETL job, like data processing job. You can use the library called Hub for loading and shuffling the data. You can use Horovod on Ray for training and actually use RayTune within the same Ray cluster. Before going into the next section, let me actually explain what was the previous limitation Ray had in order to support this kind of end-to-end ML lifecycle. So Ray was really ML focused at the beginning. And although it was good at running ML workload at scale, the data processing support wasn't good enough because the systems didn't have enough features, didn't have some necessary features to support large scale data processing. And it's been improved a lot over the last half year, and that's what I'm going to talk from now on. So before we actually talk about these architectural improvements we've made, let's see what has been enabled after this robust data processing support on top of Ray. The first thing that was enabled is the stronger third-party integration. So for example, the Desk on Ray now has a much stronger scalability and performance. And we actually have seen very high performance in really large scale, like 4 petabyte of data processing. We actually have seen 4 times cost saving compared to the regular Desk distributed backend. And also the Mars, which is the library developed by Alibaba for scientific data processing. They decided to have the first integration with Ray as well. So another benefit is the interpolability between ETL feature processing and ML training workloads. It became much more smoother. For example, you can use Spark on Ray or Desk on Ray in the same cluster as the distributed PyTorch or TensorFlow. So you can actually run the training and feature processing in the same cluster. And it's also possible to use these things with other kind of native training libraries like XGBoost on Ray. So in conclusion, it became much smoother and it became possible to make Ray in charge of distributed end-to-end ML computation with various libraries that satisfy your need. Like, for example, you can use different libraries for training, different libraries for tuning and data processing, and etc. Then let's say the short real world example. In this code example, we are going to use 3 different libraries. So Modin, known as a distributed pandas on top of Ray. By the way, note that you can also use just Desk on Ray in this case. And XGBoost on Ray, which is for distributed XGBoost training, and also RayTune for hyperparameter tuning. So this is one of examples that enable the training and data processing in the same job. So at first, you connect to the Ray cluster using ray.init, and you get the column names and import Modin. So Modin actually supports exactly same API as regular Panda. So if you just use the Pandas API, you can actually think Modin is going to be in charge of the partitioning and the distributed data processing. So in this case, you're reading the CSV file using the Modin library. And then you partition this column data for the training and validation. Of course, you can have the testing data set. And you pass this data frame into the data loading abstraction for XGBoost on Ray, which is Ray dmetrics. And as you can see from here, you're basically running the training. And this XGBoost on Ray basically runs the training job and at the same time runs the hyperparameter tuning to find the best hyperparameter for this machine learning model. So it's the diagram that explains what's happening under the hood. So as I mentioned, when you use Modin with CSV, basically it's doing arbitrarily fine-grained partitioning. And this data is passed into the XGBoost on Ray, and each actor is working as a trainer, and they're training the model while they're communicating with RayTune. So then let's dive into what we've done over the last year and see how Ray has evolved to support large-scale data processing. Let me first go through what types of data processing is out there. The most common workload is the ETL type of workload. Usually people write the jobs that run like over many hours, which basically extract the data from some file or some other data sources, transform them into different format that are more useful for their purpose, and load them into the different outcome data source. There's also one of other common example is this kind of ETL result is going to be streamed into the ML training, which is called data ingest. So sometimes you want to, or you basically do feature processing, and the processed data basically needs to be fed into the ML workload. And this is called data ingest type of data processing. And of course, you have other type of data processing like analytics, which you're the data scientist and doing more interactive analytics using like SQL, R, Jupyter Notebook, and etc. And also streaming processing, which has different type of requirements for systems. And there are many, there's a great system like Flink that supports this. For Ray, we'd like to make sure Ray be the best choice to run ML workloads. So we focused on the supporting ETL and also data ingest type of workload, which is the most common type of workload for machine learning. So ETL is used for feature processing mostly, and ETL to ML is really, really common type of workload. This presentation will mostly cover how Ray satisfy requirements to be robust backend to support the first two type of workloads, because the other two has like a different requirements. And while we are going to support them in the long term, that they're not our main focus in the short term. So the talk is mostly cover about the first two use cases. Okay, then let's actually think about what are the important features that data processing backend should support. Firstly, it should support seamless distributed execution, and also it should support robust distributed memory management. So then how did Ray look like before? It satisfied the first requirement, but not the second one. Let's actually dive into more details. Ray is designed to be highly performant general purpose systems. That says it was great at distributed execution. It has really simple and straightforward execution model and also APIs, and it's built with scalability and fault tolerance in mind. And also coming with the distributed object store, utilizing the shared memory, which basically makes the memory usage very efficient. And it also keeps the high performance even in large scale. The scheduler is not going to be bottlenecked because it uses the decentralized scheduler. Conversely, it didn't have the robust distributed memory management because Ray was primarily focusing on ML workload before, which usually doesn't require memory intensive workloads like ETL jobs. There are three known problems. The first thing is the scheduling doesn't consider memory usage or locality information. And the workloads could fail when there's the data size that is bigger than the memory capacity in the cluster. And Ray cluster was crashed or deadlocked when there's the large memory pressure. To make sure Ray supports large-scale data processing well, we wanted to make sure to have this robust distributed memory management layer and solve the problems I just stated. The approach we took was to actually build the simple distributed shuffle workload. And we wanted to make sure this works really, really well on top of Ray at large scale. So actually, let's see what distributed shuffle means first. In the distributed systems, data set is usually stored in partitions, with each partition holding a group of rows. And shuffle is basically the operation over this data set that redistributes data across each partitions. It is a really important operation because a lot of distributed data processing algorithm use this as a primitive. For example, distributed sort needs distributed shuffle behind the hood, like something like join or something like repartition. They are actually work like a data processing algorithm that requires distributed shuffle as primitive. Then why did they focus on distributed shuffle? It's because the distributed shuffle stresses the data processing system's memory management layer. So if we can make sure this is working very well, then we can make sure our memory management layer is robust enough to support large-scale data processing. It's because in distributed shuffle, it's very common the data set size is way larger than the memory capacity in the cluster. And also, shuffle basically requires to shuffling all the data over the network in the system. So it basically needs to stress the system a lot. So then how does shuffle work? As you can see, shuffle consists of map and reduce phases. each circle means task, and each square means objects. And as you can see, these objects at each map task is going to stream over to the reduced task, and they're shuffled here. So this is how the distributed shuffle works. Then let's start being equipped with how Ray's distributed object store works before actually we go deeper. Let me introduce then Plasma Store here. So Plasma Store is the built-in shared memory distributed object store that comes with Ray for free. It was originally developed by Ray for the shared memory performance optimization and contributed to the Arrow project. And we backported again for further optimization in this layer. Also, Plasma Store, as you can see, the first characteristic is there's Plasma Store per machine. And you can think they're local only. And they stores the Ray objects in the shared memory. And whenever there's a task that needs object A, for example, this object A is basically in shared memory store. And we support zero copy read, so each of tasks doesn't need to actually copy them into the process memory to use this object. So this can mean use very efficient memory usage. And Plasma Store also pull and push objects on demand. So let's say you have two machines and the task requires object A. And in this case, machine B needs object. So in this case, machine A is basically pushing object to machine B. So this task can actually use this object in this machine B. Then let's start looking at some architectural improvements we've made to support distributed shuffle at scale. The first improvement we made was to improve scheduling. Originally, Ray didn't take into account of locality information when scheduling. And we realized this caused a couple issues. So before explaining more about this, let's actually see a diagram. So this is the example when there's no locality over scheduling. So as you can see, this task requires object A, and object A is in machine A, but task is scheduled on machine B because let's say it doesn't take into account of this object location. Then in this case, in order to execute this task on machine B, we need to push this object and have unnecessary copy. So in this case, if we can support locality over scheduling, we can have much better memory usage in the cluster because this task is going to be scheduled on the machine that already is object A. So the object A doesn't need to be copied to other machines in the cluster. So now Ray Scheduler is doing locality over scheduling. And it basically calculates which machine will have the biggest input size. So input, when I say input, it's this input. Biggest input size that is already cached in each machine, and it's going to be preferred to that node when it's scheduled. Another improvement we've made is called memory over scheduling. So Ray always try to schedule tasks to nodes that has the low memory usage. So let's imagine this kind of scenario. You have machine A and machine B, and machine A uses more memory than machine B. So in this case, we always try to prefer the machine B. So the real algorithm is a little bit more complicated than this, but this task is respecting the locality information and also trying to be scheduled on the machine that use low memory usage, so you can actually distribute the task properly in the cluster. So the second improvement we've made is to enable out-of-core data processing. For people who don't know what that means, out-of-core data processing is processing data that is too large to fit into a computer's main memory. So in order to support this, we developed a feature called object spilling, which basically spills Ray object from object store, the shared memory object store, to the external storage like disk or S3. So let's actually see an example how this object spilling works. So this is the same shuffle example I demonstrated before. It's like much simpler diagram. So imagine this kind of map and reduce phase. And in map phase, you basically create the object in the shared memory. And in the reduce phase, this reduce task shuffle the data. So it gets the data from each map task. Then how they work with object spilling, let's actually see from the map phase. So it's the same as this part. So at first, this is how the cluster looks like normally. So you have machine, so node is same as machine. And this gray square is the process. And you can schedule task here. And this is the shared memory object store, which is Plasma Store. And you have the external storage like this. So let's imagine we have this map and reduce phase. in the shuffle. So in the map, it basically creates these objects, and they're first scheduled on each of worker process, and they create all the objects. So now we need to schedule more map tasks, and you just realize you don't have enough memory. So in this case, you just spill the objects and you fill this up. So let's actually see what happens in the reduce phase. As I mentioned, this is same as this phase. Each of this reduce task gets the object. So these objects are shuffled in the reduce worker. So this is the state from the previous one. Now this reduce tasks are scheduled on the worker process, and it needs to get these 4 objects. And this one needs to get these 4 objects. So it's trying to get the object. And before it gets the object, it has to spill them because it needs more memory capacity in the shared memory. So it basically spills the objects that are not used by this worker, and it restores the objects that are necessary from the external storage. And the same thing is going to happen for other reduce tasks. So at the end, all of your reduce task is going to have the shuffled objects in memory, and they can do some operation like sorting the shuffled data, for example. The last improvement I'll demonstrate is how we improved our memory management layer. In summary, now Ray respects a hard limit for distributed object store and take the smart actions based on this situation. This means there are three improvements we've made. First, we can now detect when there's the memory pressure. And second, based on this information, we can actually guarantee the progress when applications runs out of memory by taking actions that are needed to make more space. For example, we can evict unnecessary objects, or we can spill objects that are not used right now. Lastly, each of machine now has admission control when scheduling tasks, so they limit the max amount of memory it is using. In this case, we can avoid machines are over using memory. We are going to dive into the third example in this presentation. So imagine the map phase just completed and it spills all the objects. And now there are 2 reduce tasks scheduled, and this task needs 4 objects, as you can see. So it's trying to restore 4 objects to the shared memory object store. And it happens concurrently. And as you can see, these last 2 objects are not restorable because you don't have any more capacity. So this is deadlocked. So as you can see, this needs this light color 4 objects, but you don't have enough space to put this light color object for the first task, and same for the second task. So in this case, what can happen is you can evict this like a object and bring this in. But if this is not smart enough, imagine this thick blue is actually evicted and this thick orange is added, then you're basically in the same situation. This thick blue needs to be restored again. And there are situations like this that can happen commonly if you don't have smart actions based on your memory usage. So then how did it solve the problem? So now Ray's decentralized scheduler is also working as a decentralized memory manager. So it is aware of memory and do proper admission control based on the memory usage. And it always trying to not use memory more than its capacity. So this means Ray doesn't schedule tasks if the object that task require use more memory than the capacity of machines. So let's actually see with the real example. So in this case, unlike before when we try to restore the objects concurrently, we now know that if we restore all the objects for this and this at the same time, we don't have enough capacity in the shared memory. So we only try to restore object for the first task. And once first tasks are done, the second task also needs to restore the object. And at that time, we also try not to restore object for this task because we know if we do that, we're going to be deadlocked. So do the same thing, and we basically repeat until every tasks are scheduled. So there are tons of other progress we've made, and if you're interested in more technical details in this layer, please check out our white paper. The link is available in the slides. So after all the improvement, now Ray has both features for distributed data processing engines. So it has seamless distributed execution, which it already has before. And now it has robust distributed memory management layer, which is going to make this whole memory management better. Like you use less memory, you always in progress when there's a memory pressure, and you are able to process data that is larger than your memory capacity. And now, as another note, we recently succeeded to run 100 terabyte distributed shuffle on top of Ray after all the improvements. And we are now planning to improve actual sort and see how much performance we can demonstrate from there. Yeah, thank you so much. So if you're interested in Ray, please visit our GitHub page and give a star, and or you can come to the Discourse for questions. And if you're interested in Anyscale, we are hiring. Thank you so much.